Good afternoon. Today we are going to resolve some vectors. As you saw in the vector treasure hunt, when you are adding multiple vectors together, the sum of those vectors is called the resultant, and it can be depicted by drawing a vector from the beginning of the first position to the end of the last position, and that's called the resultant. What we're going to do today is play with this resultant. We are going to break that resultant into its components, which is called resolving a resultant into its component vectors x and y. And then we are going to solve this example problem to show how resolving the vector will give the overall displacement of any object. So the example problem we're going to work through in this video is, in order for you to get to your next class, we'll pretend you have to walk 5 meters in the direction of 60 degrees north of east. Then you're going to walk east 7 meters. What is your displacement? So where I got these directions from was I pasted a polar coordinate grid on the right-hand side, so you can see that the purple vector lines up with 60 degrees north of east, going this way. And the 7 meter vector is pointing directly east, and remember in polar coordinates that east means 0 degrees. So in order to find the magnitude and direction of a resultant, we resolve the resultant into its components. So here's my resultant again, from the tail of the first vector to the tip of the last vector. And when I resolve this vector into its components, I have to realize that it's going to be made up of the x component of my first vector plus the x component of my second vector, and the y component is going to be, in this case, just the y component of the first vector, because the second vector is just moving to the east. So these two purple dashed lines are the x and y components of my first purple vector that's 5 meters long, and this red dashed line is the x component of my red line, which is 7 meters long in my diagram. So I have to realize that every single one of these vectors can also be resolved into a right triangle. So I did this down below here. This piece at the bottom of your screen is probably the most important thing to write down in this video. In fact, I highly recommend at this point that you pause the video and write down these relationships, because these relationships are not going to change throughout this unit. I'm saying this unit because there's going to be a twist next unit. I'm sorry. If you come back after you've paused, then you will be able to see where I get these x and y components from. So if I move this vector down to my little right triangle, I will see that it's the adjacent leg of the right triangle that I've formed here. Well, the relationship between the adjacent leg of a right triangle and its hypotenuse is cosine. So to find this x component, I can use the relationship that cosine theta equals the adjacent side x divided by the resultant r. Rearranging, x is going to be equal to the resultant times the cosine of the angle. And that's good for this unit to find the x components of any vector. I can do the same with the y component. Here's the y component here. The y component, its relationship to the resultant is going to be sine, because sine is opposite over hypotenuse, so the sine of theta is y divided by r. I can rearrange this relationship to say that the y component is the resultant times the sine of the angle. This is always going to work for you in this unit. So let's see how that works for our sample problem. So here we are again with my sample problem. Let's draw back in my resultant from the tail of the first vector to the tip of the last vector. And let's find the first x component. So in order to do this, I'm going to use the relationships that I just found on the previous screen, that the x component is going to be equal to the length of the vector, which is 5, times the cosine of its angle, which is 60 degrees. I did a bad job of sig figs on this video, so I'm just going to round to the 10th spot today just to make it easy. And I'm going to say that the length of that x component is 2.5 meters. So this little guy right here represents a vector that's 2.5 meters long. Let's do the same for the red vector. I'm going to have x equals, in this case, 7 cosine, and this time it's going to be 0 degrees. The cosine of nothing is always going to be 1, and there's a math reason for that. Ask me if you want to know. And we're going to call that 7.0 meters. You can put these into your calculator, pause the video, put them into your calculator, and double check my math. And let's just add them up right now. In order to get the total x component, what I mean is this purple vector plus this red vector. I'm going to add 2.5 times 7.0 to get 9.5 meters. I called that green on my screen because I'm going to change the color here to say that this whole x component now, which is in green, is going to be 9.5 meters long. Now we're going to do the same with the one and only one y component. Remember, the only y component in this video is the one from the first vector, because the second movement, the second vector, is just horizontal. It has no y component. It doesn't go up and down at all. So what I'm going to write here for my y component is the y component of the little purple vector is 5 sine 60 degrees. And solving that out with my poor sig figs, I get this to be 4.3 meters. Do the same with the red vector, and I'm going to do it the long way. You can type into your calculator the sign of 0 and prove to yourself that it's 0, but the sign of 0 degrees is nothing, because that particular angle will not go up and down at all. It will have no vertical component. So this is going to be nada, 0. So I'm going to add those up. 4.3 plus 0 is 4.3 meters. So what I've just found here is this little purple component, which, just to be consistent, I'm going to turn it into a little green component, is now 4.3 meters long. So you can imagine what I'm going to do next. What I'm going to do is I'm going to find the hypotenuse of my right triangle by using my Pythagorean theorem. And I'm going to skip some steps here because I know that r squared equals x squared plus y squared. So you can find the resultant vector by using the formula r equals the square root of x squared plus y squared. And then I'm going to fill in the blanks. I'm going to have the square root of 9.5 squared plus 4.3 squared. And I'm going to find this whole thing after rooting to be 10.3 meters. Excuse me, 10.4. So what I've just said now is my resultant is 10.4 meters long. So that's how far I need to walk to my next class. Well, what about direction? Let's go to the next screen and look at direction. But before we go to the next screen, what I would recommend that you do is you pause this video and review what you see here to make sure you understand why it's important to resolve vectors into their components and use those components to come up with the magnitude of the resultant. So let's find direction now. What we found was that we've got this x component at 9.5. We've got this y component at 4.3. You found that your resultant's magnitude is 10.4. You've got a whole bunch of options here. So I'm going to use the option the book uses, just to be consistent, where I'm going to find the tangent of this angle. And I'm going to use tangent because I've got the opposite, which is the y component, and the adjacent, which is the x component. So I'm going to have the tangent of theta equals 4.3 divided by 9.5. I'm going to inverse tangent both sides. And what I find here is that theta ends up being 24.4 degrees. Now, if I'm using polar coordinates, I'm going to say 24.4 degrees north of east, because I'm raising vertically 24.4 degrees up from east. If I'm using compass rose coordinates, I can subtract this from 90. And what I end up getting is 65.6. And this one we can call east of north. They're the same direction, two different ways of looking at it. The second way of looking at it has to do with my compass. This is my compass method. And the first way of looking at it has to do with polar coordinates. I'm going to put a P here for polar, and I'm going to put a C here for compass. If you put either one of these on the test, I'd mark you correct, because they are both correct. One of them you can use a compass in the woods. The other one you can use polar coordinates in a math class. Both are correct. So at this point in time, again, I recommend rewind, rewatch, and then go forward and do the problems that are on page, I believe they are on page 92, 1 through 4, 94, 1 through 4, and we will be prepared to talk about these on Friday. Don't forget to comment on the video down below. Rank this video 1 to 5. Thank you so much. Have a wonderful evening.